Heisenberg uncertainty principle explained. Hopefully. Suppose you prepare a particle in a quantum state psi. In quantum mechanics, we write psi in these brackets, and that's how we describe the quantum state of the particle. You now want to measure its position and velocity, or better, its momentum. You prepare the particle in the same quantum state psi 1000 times, and each time you measure its position. Your measurements will have a mean value x and a standard deviation delta x. This tells you about the uncertainty of your measurements. You then make another 1000 experiments, like you did before, and this time you measure the momentum of the particle like you did for the position. You'll get a mean value p and a standard deviation delta p. Note that it's not possible to measure position and momentum simultaneously, as the x and p operators do not commute. That is, they do not have a common base of eigenstates. Hold on, what's that? Experimentally, you may think these as needing two different instruments to measure position and momentum which cannot run at the same time, so that you need two independent measurements. When measuring the position, you are altering the system, so that after the measurement it is not in its initial state psi anymore. For example, it is in a precise eigenstate of x. Same if you were to measure the momentum first. Delta x times delta p equals some number. Let's call it k. Now you ask yourself, can I prepare my system in a more precise state, such that the new uncertainty on x times the new uncertainty on p is smaller than this number? The answer is yes, until you reach delta x times delta p equals h bar divided by 2. Heisenberg uncertainty principle states that you cannot go lower than that. Note that we have been assuming that the uncertainties of our measuring tools are negligible, meaning that delta x and delta p have nothing to do with the error of our measuring tools. Instead, it is something intrinsic to quantum mechanics. While in classical mechanics a particle would have a very well-defined position and momentum, so that the uncertainty only derives from our ability to measure a property more or less precisely, in quantum mechanics that is not the case. Before even doing any measurement, the quantum particle does not have one position and one momentum, but it's in several places with several momenta at the same time. It may have one very well-defined position, but then it would be in a superposition of lots of momenta, and the uncertainty on the momentum would be infinite. So the quantum uncertainty does not depend on our ability to measure the position or the momentum of the particle. It's an intrinsic property of the quantum particle, which does not depend on our measurement. The mean value of the position x tells you that if you were to measure its position, most of the time it would turn up around x, within a range delta x. These are the most probable values of the outcome of your measurements. Likewise for p, if you were to measure it, the particle would be found to have momentum p within a range delta p. Going back to the inequality we wrote before, delta x times delta p greater or equal to h bar divided by 2. If delta x is really small, then delta p must be large enough to compensate, so that the overall product is greater than h bar over 2. And after all of these, let's end with a joke. So Heisenberg, Schrödinger, Ohm, and Einstein are in a car. They get pulled over. Heisenberg is driving and the cop asks him, "Do you know how fast you were going?" "No, but I know exactly where I was." Heisenberg replies. The cop thinks this is suspicious and orders him to open the trunk. He checks it out and says, "Oh my God, do you know you have a dead cat back in here?" "I do now, sir," says Schrödinger, to whom Einstein replies, "This story looks incomplete to me." The cop moves to arrest them. Only Ohm resists.